Good morning. As you know, I've got a long list of requests. Well, good morning, and I've got a very long list, 10 pages, of requests to review the participation, so I will, as soon as I find a couple of quiet hours. And some students still haven't picked up the exam. Maybe they never attended a lecture since. Maybe they aren't curious at all, or maybe they find me too intimidating to ask for their own exam. If it's latter, if you think you can walk through your professional life without meeting intimidating people, you're up for a big surprise. So, we talk about pressure, and that's an official definition of the pressure, and this is how we can calculate the gauge pressure. The pressure due to certain amount of material above the level where we're measuring the pressure. And if there is another type of material, like gas, atmosphere, that adds its own pressure. And two things about pressure. Number one, it doesn't depend on the direction. If we use a simple membrane manometer, if there is a membrane which feels the force acting on it, force divided by area is pressure, so we can read the pressure, and if we insert it and move up or down, we can see how pressure changes. But if we keep it at the same level and just start rotating, no change. And another important fact is Pascal's principle. If we exert the pressure somewhere in that fluid, it transmits everywhere through the fluid. And this principle is used, for example, for different mechanical machines like hydraulic lift. Here and here, we neglect the gauge pressure, actually. It's practically the same level. But if we apply an external force, force over area, gives the, yes?
How can pressure not have a
Because of a definition. It's just a good question, because technically what should I have said is, you see, there is no little arrow above that letter. So it is automatically assumed no little arrow, hence the magnitude. But we are too lazy to write all those symbols. We just write capital F, and we assume it's a magnitude, which is a number. And we do that because of this experimental fact. Because first, we have measured it, and the experiments show no direction, but same magnitude. That's why we use the magnitude of the force as a definition. Good question, thank you. And so here, if we apply a force, we exert a pressure, and exactly the same pressure transmitted to a different place, and again now the same pressure exerts a different force, and this is how we can generate a stronger force. This is an equivalent of a lever arm, basically. But of course, when we win something, we lose something. Same situation is here, like we had with the lever arm. We have to push through a longer distance, which might take more time. So nothing is perfect. Now, we actually have a mathematical means to prove, to derive the expression for the buoyant force. You don't have to do that. That's just for me. I love it. But we know now that if we immerse an object into fluid at different levels, that fluid exerts different pressure. Side pressure exerts side forces, and those forces cancel each other out. So the force from below is always stronger than the force from above. We can calculate the net force. And the calculation, of course, gives exactly the same equation which we used before. Well, it's basically pure algebra. Now, we know that the atmospheric pressure is large, and the first time it's been measured many, many years ago in Italy. Evangelista Torricelli, he just was one of the first one who was able to manufacture a very long, relatively long glass tube, so long enough to see that if you fill it up with mercury, flip it over, place it in the mercury again, not all mercury leaves it. Why? Well, because the atmospheric pressure balances out the pressure inside, and he measured it in his own units, which is the length of this mercury column, millimeters of mercury column. But now we also call it 1 atmosphere. It could be measured in different units, pounds per inches squared, or Torricelli's, which is millimeters of mercury columns. And this is a very large number. And if we calculate the amount of force acting on just a square meter, that's going to be thousands of newtons. Our skin actually covers more than square meter on average. So this is how much force do we experience, everyone from us in this room. So the question is, that's the question. These are answers. There is one answer which doesn't make any sense. That's the answer number 5. It contradicts all other answers, technically possible. So keep choosing yours. And I want to demonstrate, as I promised, how strong the atmospheric pressure actually is. There are several classical experiments on this matter. But first we need a device which can move air in one direction or another. We call it a pump. So the air pump needs to be used for all these demonstrations. And what do I want to do first? Let's say this. This is a demonstration which describes what happens with an object if all air is getting sucked out. Pump. Valve. Literally a matter of seconds, and it crashed. Literally. Due to the atmospheric pressure. But this, good for us, is not happening to us. Why? What do you think? Anybody? Exactly the same force kind of acts on us from the same air. Not us. Yes. Yeah? And why do we have it? How does the air get inside us? Only? We have eyes, ears, we have many, many holes, pores, which is good for us. Because otherwise, that's what would happen. Well, the next, also very old experiment has a name, Magdeburg's hemispheres. Well, first of all, even the human lungs is enough already to keep them together. And it, the card. No. Well, I can attach a weight to it or pull a scale. You have to apply a relatively strong force already. So what's going to happen if it's not a human person, if it's a pump which sucks the air out? Do you think that on the left, or well, on the right for you, is a picture or a photograph? What do you think? See? 8 horses on the left, 8 horses on the right, trying to pull apart 2 hemisphere, and they can't. And that happened because he, Otto von Guericke, he perfected first pumps. He was able to create relatively low pressure inside, well, spheres, hemispheres, and okay, good. Yeah. Anybody want to try? All right. Could you please pass it to the gentleman behind you? Yeah, on the second row. He helped me last time. Anybody? All right. Now we have professionally manufactured hemispheres like this. You can go to a hardware store, just try to pull it and give it to somebody else, but don't steal it, please. So, all you have to do is this. Same principle. What happens? Well, now, when I press them together, there is no air between these, how do you call them? Suction cups. So the air pressure from the outside is acting on this area only, but the force is so strong that a human person cannot separate them. And there's one more demonstration which I like to do. However, due to certain features, it doesn't work 100% because, well, I'm going to explain why. But it is a really good demonstration when it works. It is called air cannon. So basically just a piece of PVC, just a tube. All I need is a ping pong ball. Put it in. But now I have to seal it up because I want to suck the air out. The problem is that sometimes a tiny piece of tape gets stuck to the ball, and the ball, because of that, gets stuck inside. So to prevent this from happening, to decrease the risk of that, I have to use some material to decrease the area of the tape which might touch the ball. This is also a good illustration of a difference between theory and practice. In theory, everything should work. How to make it work in practice? That's much more difficult question. All right, let's hope this will help. So the first one, actually, just in case. Don't be scared. Second. And I need to see the ring, because if this piece is too large, the tape doesn't touch the tube, so it's not getting sealed. So many little things which make a big difference, exactly like in life, right? All right. Now it is ready, so I have to attach it to a pump. Now I want to catch the ball. Okay, so I am ready. It's going to take about 90 seconds. Okay, I feel like membranes get sucked in. My phone is there. I usually use it to time. All right. How many Mississippis has passed already? No? Does it feel like a minute? All right, let's wait a little bit longer just in case. I want to make sure. Now, I will have to puncture that seal to let air rush in. When air rushes in, what does it mean? A boom. It creates an explosion. That's why I have these. You don't? So what do? Exactly. So be prepared for the boom, at least, at the minimum. It was the boom, but the ball remained inside, yeah. Well, in a case like that, I usually try the demonstration every day until it works. It worked yesterday. So, yep, it's stuck right in the middle. A tiny piece of tape holds it. Well, you're not in luck today. Moving on. I promised I would do it. I did it. I said it wouldn't work. It didn't. I was right both times. Life happens. Be prepared. Not everything goes according to the plan. Well, and this is why an astronaut needs a spacesuit. Because without that, in the outer space, that's what would happen. We would explode. Here, our internal pressure and external pressure balanced out. As soon as this balance is broken, that's it. We can explode or we can be crashed. Well, we are done with static fluids, and now we're moving on to the dynamics of fluids. And of course, we consider only the easiest situation. Bless you. An ideal fluid with no internal friction, a fluid which has no friction between the fluid and the tubes, and there is no turbulence. We call it laminar flow. So, and also it is incompressible. That's very important, because if we cannot compress a fluid, that means inside the pipe, every second should travel exactly the same amount of it. That's it. So in this situation, let's say you have a pipe with a different area inside, so we can connect it. It's just two ends of the same pipe. So the same amount travels everywhere, which means the same amount of mass or volume which enters a pipe at one end should leave the pipe at another end in the same time. And how do we calculate the amount of material? Well, density times volume, or delta volume in this situation, if I write it. And how do we calculate the volume? Well, in this situation, it's a circular pipe. Let's say it's circular. It doesn't really matter. And the fluid travels this distance in a certain time. So the volume will be equal to area times distance traveled, because for this cylinder, that's the height of that cylinder. And if we want to calculate the amount traveling every second, we just have to divide this by time. First of all, this is a definition of so-called mass rate flow. How many kilograms traveling every second? That's what it is. Now we can see that according to our analysis, it should be equal to the product of three variables: density, area, and the speed of the flow at that location, V1, for example. And as we said, that should be the same amount everywhere, so we can write it should be constant through the pipe. So this equation expresses two important facts. Number one, how to calculate mass rate flow if we need it. It is equal to the product density, area, speed. And the second fact, inside the pipe, it remains constant for an ideal fluid. Now, the density of an ideal fluid is also constant. So what I can do is I can divide this expression by density on both sides. On the left, I have product A times V. On the right, I have another constant. Still constant. A constant divided by a constant is a constant. Now, this product tells us how many liters or cubic meters traveling every second through any cross section of a pipe. So that's what we call the volume flow rate. And this is actually mass flow rate. Yeah, sounds better. Well, so these are calculations, and this equation, the last equation, also has a special name. We call it a continuity equation. But basically it says the volume flow rate remains the same, constant, through the pipe. It's, in a way, the law of conservation of amount of fluid. The amount travels. Of course, it's an ideal situation. Now, let's say the fluid travels through pipes, and if there is no friction, we have to say that energy mechanical energy should be conserved, or it can be changed by non-conservative forces. Well, in this situation, that non-conservative force which makes a fluid flow would be an equivalent of this guy pushing himself. And how would that change the law of conservation of mechanical energy? Well, it wouldn't. If we want to calculate change in the kinetic energy, it's just one difference between an actual object and a fluid. An actual object has a special size, normally small enough. A fluid could be continuous, so we have to choose a specific part of that fluid to analyze. And of course, it's 1 cubic meter because it's one in international system of units. So we can calculate how kinetic energy of 1 cubic meter changes. And of course, change in the kinetic energy should be equal to the work done on it by what? Well, in general, if fluid changes height, gravity might do work. Plus, that extra pressure due to pumps, for example. But it's easier to rewrite the same equation in terms like variables related to one location and variables related to another location like we used to do. So this equation now relates kinetic energy, potential energy, and the pressure inside the pipe at one cross-section, and kinetic energy, potential energy, and the pressure at another. And the law of conservation of energy says they have to be the same, but this has a special name, Bernoulli's equation. He used it first to describe different phenomena in fluids. So these are two equations which we can use to describe anything happening with an ideal fluid. In particular, static, we just have to set speed to 0, and we get exactly the same results we had before for the static fluid. So this is an equivalent of law of conservation of mechanical energy, an equivalent of work kinetic energy. This is the law of conservation of amount. That's it. Physics of the ideal fluid is on this slide. Question? So this device has a name, a venturometer, and this is just a copy of the device. And I'm going to make the air flow through this pipe. And as you can see, we have two different parts here. Well, let's say part number one, when this tube is connected to two locations with exactly the same diameter. And number two, when two tubes located to locations with different diameter, wider pipe, narrower pipe. So this room has the air source built in. And now we should see this picture. Same level and different level. You have to do it slowly, because sometimes some people forget, open it quickly, and it shoots the water at the students. So question now, of course, about the pressure at points A and B. And I want to see the distribution. That's a question number 3. So, okay. And this question has no relationship to yet to any equation. This is a common sense, basically, question. And common sense seems winning. So what do we have here is a case of a fluid which was initially in equilibrium, so same height. If I want to change the height, what should I do? Well, I have to put some pressure. So if I press on the bulb, more pressure moves this level down, less pressure up. Which means in that experiment, again, when you see the level lower, that means there is more pressure there. And the answer is 3. But now we have means to prove it mathematically. So let's do it as an exercise. Well, this is the first situation. And we have two equations which we always can use. The first one, short one, the continuity equation. The second one, the longer one, the Bernoulli's equation. Now, for points C and D, the area is the same. How do we know? We can see. We have eyes. So, this equation tells us that if I use this fact, well, let's write C and D. I can cancel the area because it is the same, and that tells me the speed will be the same. Now we can use this fact in the Bernoulli's equation. If the speed is the same, we can cross out kinetic energy. Plus, of course, for the horizontal pipe, the height is the same. So what's left? The pressure also is the same. The pressure pushing down on both surfaces here is the same. What do we do to relate pressure A and B? Exactly the same thing. Nothing else can be used. Only two equations. The continuity equation, and I can write A and B immediately instead of 1 and 2. And Bernoulli's equation. That's the hardest part, writing down. All right, done. Now, we have to look at the picture, use our eyes and common sense to make a statement about the areas. When we need to compare two numbers, we have to make a choice between only 3 possible options. And clearly, the area A is greater than the area B. What does it tell us about speeds? Well, now you can compare two numbers, speed at A and speed at B. Every time when we need to compare two numbers, we have to make a choice between only 3 options. So please tell me now, what option should I choose to compare the speeds? This? If you think that is correct, nod. If you think that's wrong, this? No. The relationship between the speed A and speed B is given by the continuity equation. Let's say I want to calculate speed B over speed A. That will be equal to area A over area B. And this should be what? Greater than 1. Because area A is larger, area B is smaller, like 4 divided by 1.7. Which means, if we solve it back for the speed, speed B should be equal to, should be greater than speed A. Larger area, slower motion. That's it. If you narrow it down, water molecules should travel faster in order to transmit exactly the same amount per second. But now we can use this fact in Bernoulli's equation. Again, same height, so potential energy doesn't matter. Now, this term, kinetic energy at point B, should be larger than this term, kinetic energy at point A, because the speed at B is higher. But to balance it out, this pressure should be larger than that pressure. Pressure at point A, and is greater than pressure at point B. And you can just do it by mathematical exercise, calculating this difference. In mathematics, if you calculate the difference, you have only three options. Sorry, three. Greater than 0, equal to 0, less than 0. And if you calculate difference pressure A minus pressure B, I'll try to fit it in here. Pressure A minus pressure B, it should be equal to density over 2 speed B squared minus speed A squared. And because speed B is greater than speed A, this will be greater than 0, which proves the fact that pressure A is greater than pressure B. So we know it physically. Now we know that, of course, we can prove it mathematically. This is just an illustration of how these two equations work together, always. So point C and D, point A and B. Now, we just said that for a horizontal pipe, the faster moving flow means lower pressure. And that means we can generate a pressure difference. Well, this is not new, push it up, but what about this? Why it doesn't fall? Let it, you can keep it. It likes you. Why did it fall? Because at the bottom of this ball, because of just friction between air and the ball, it traveled slower, so the pressure from air on this ball here was higher than there, and there is a force which pushes it up. And it actually may be really strong. So this is a golf ball, which is much heavier than that plastic ball. Why it didn't fall when the air was traveling fast? Because the ball was obstructing air here, so it was traveling slower above and faster below. faster above and almost not below. Pressure was pushing up. But when I turned it off, eventually, the pressure difference couldn't provide the force strong enough to compensate for the force of gravity acting on it. And what I like the most is this demonstration, because it's loud. I used to teach at 8 o'clock, not at 8:30. Loud demonstrations at 8 o'clock, the best. I just need a big ball. It is strong. I'm getting a little bit rusty. Okay, one more time, and if it doesn't work, I'm going to move on. Not my day today. It's Friday. No one wanna work on Friday. Anyway, the point is, this is how we fly. And the principle is described by the Bernoullis equation. Below the wing, due to Bernoullis equation, the pressure is much higher than above, and because of that, the lift force is so strong that it can lift very, very heavy objects. And now, formally, we are done with the theory related to fluid dynamics. We're going to do more examples, but first, we're going to do some more theory. So you could use that over the weekend to solve more homework problems. It's actually a very simple theory because we know almost everything about gravity except one equation which we're learning right now. We know that gravity pulls objects together. We know that it is a force, and every time when we say this word, force, we have to draw a free body diagram. We have to treat forces as vectors and calculate the net force. Net force is related to acceleration, so we know everything. And the only new equation here is the Newton's law for gravity. He discovered it by analyzing the motion of the moon. And now we can use it to calculate the strength of the gravitational attraction between any two small objects or spherical objects. If we have two small objects, this variable r just represents the distance between those objects. But if we have a large object and a small object, yeah, probably I have to take that ball back. Sorry. Thanks. Yeah. So one object and second object. In that case, we have to measure distance between the center of the big one and neglect the side of a small one. And if we have two large objects, we have to measure distance between the center of the first and the center of the second. That's what this r is. And also we know that gravity does work. And we know that potential difference between initial potential energy and final potential energy is equal to that work. However, what we used for calculating potential energy, mgh, is not an exact expression. It works only when an object is close to the surface. In general, we have to use a different expression, a little bit more complicated. This is the exact way to calculate potential energy for gravitational attraction between two objects. So that's the theory. Now, the most important application of this theory is satellites. If we have a satellite orbiting a planet or a planet orbiting a star, we can start from a simplest model, motion, a circular motion with constant speed, or we call it a uniform circular motion. And what do we know about uniform circular motion? Everything. What do we know about Newton's second law? Everything. And now we also know everything about Newton's law of gravity, which means now we are done with this theory. I just want to ask you a question first. Here we have a small satellite orbiting a large planet or a star. People call it a central object or a central mass because it's at the center of that circle. This is a photograph, a snapshot of this object close to the central mass. And the question is, what is the direction of the acceleration of that small satellite at this very instant, at this very location? So you have to choose, you have to enter. I want to check. This is question number 4. So sliding down. And the answer number 4 is correct. This is a motion, which we have studied extensively, a uniform circular motion. For the uniform circular motion, the acceleration actually has a special name, centripetal acceleration. We know that the magnitude of the acceleration is equal to speed squared divided by the radius. And we know it always points toward the center of that circle. And the center of this circle is located to the right to the object at this very instant. That's it. And of course, if we want to, we can now combine all the known equations to answer any question about period, which is a time for one whole revolution, or distance from the object to the planet. We just need to remember that this distance is called height or altitude. And it's not equal now to the radius of the planet. It's equal to the radius of the planet plus the altitude. For us, for people, because we are on the surface, we could use all those equations. We just have to use the radius of the Earth if we want to calculate, for example, force of gravity acting on us from the Earth. Well, now you're ready to solve more homework problems. I know it makes you maybe sad, but it makes me happy. Now we can just, so since we have covered all theories for fluid dynamics and gravity, now we can start just solving examples and continuing solving examples next week until we switch to a new topic, And now a question about building a fountain. I'll be back. I'm back. It's a very easy to model a situation like that. I need a source of liquid. This is only to catch the water so it wouldn't splash around. We don't have to, well, treat it as a part of a problem. Yeah, it's an imaginary bucket here which catches water. Now, okay, what's going to happen if I insert this end of this tube into the bucket? What do you think? Nothing. Second question, why is it blue? You know that some people have red blood and some people have blue blood, but that's a dye. So nothing, of course, nothing can happen. First, I need to make this water travel all the way down, and then it will keep itself moving. How do I make this to happen? It's not blood. All I have to do now is just turn it up, and this will be my fountain. And this is how you steal gasoline from your enemy. Erase that. So, of course, my experiment doesn't involve an ideal fluid. There is a lot of friction here. But ideally, if we don't have any friction, that means the energy, mechanical energy, should be conserved, and mechanical energy is kinetic plus potential. So if we look at any single water particle, we can take a die, place it, and see how it moves. Without friction, it actually should move no different from a person riding a roller coaster. That's it. And for the person riding a roller coaster, if it starts from initial height and it goes down, it should reach the initial height and stop there. There's energy conservation. Well, of course, we have means to actually calculate the speed, and if we know the speed at the point where water leaves the hose, we know the speed. We can calculate when it stops, because it's like shooting a ball. The final speed should be equal to 0. So this is our immediate goal, to calculate the speed at the point number 1. And to do that, we have to relate two locations, technically any two locations in this fluid. Well, it's water. And two most convenient locations are number 1 and number 2, because they both are open to the atmosphere. If it's open to the atmosphere, that means the pressure should be atmospheric, which makes just calculations easier. Now we can write two equations, of course, the same two equations. Fluid dynamics requires writing two equations. The continuity equation and the Bernoullis equation. And now it's a very rare, very unusual situation in physics when we have to think a little bit. We don't know specific information about the size of this tank or the size of this tube, but we can look at the picture and we can make a natural assumption that the area of the tank is much greater than the area of the tube. So if I want to relate speed number 1 and speed number 2, I can solve the continuity equation for speed number 2, A1 over A2 times V1. But this ratio, A1 over A2, should be much less than 1. Which means this ratio, A1 over A2, is practically equal to 0. Which means this speed is practically equal to 0. Of course, in reality, it moves, but it moves so slowly. So we ignore that motion, at least for a while. That's it. Which makes our calculation easier because now we can just set speed number 2 to 0 in the Bernoulli's equation. Now, because the pressure is the same on both sides, pressure goes away. What's left? That speed we are looking for, and 2 different heights. That's it. And if we use numbers, if we use these numbers from the picture, well, we can choose the 0 level at the lowest location of this system, which is here at the bottom part of the tube, or we can choose the lowest level at the lowest point between these 2 points, which is here at the point number 1. Of course, it doesn't matter. So if I choose my origin here, height number 1 also becomes 0. And height number 2, this will be height number 2, will be equal to what number? 30 centimeters. How do I know? I can read. And the final equation, which I can fit here, says density times speed squared over 2 should be equal to density times g times height number 2. And now what we can do is canceling density. And if we solve it for the speed we are looking for, we get the equation which we already had before many times, just for a ball which was shot up and traveled distance, well, h2. And why? Because there is no friction. When there is no friction, it doesn't matter what type of a system is investigated. A ball, a roller coaster, or a fluid which moves without friction. All right, and question number 6. Now, it's about 2 different points. Point number 1, but the new point is point number 2, point B. What do you think about the speed I will ask you this question in a minute, and you will just indicate your answers by showing the number of fingers corresponding to your choice. The speed of water at point B. Now, if you think greater than at point 1, please show me 1 finger. Thank you. If you think the same, please show me 2 fingers. If you think it's lower, 3. Which equation did you use? To describe the motion of water or any fluid, we have to use 2 equations, because we have no other. So, if you want to answer the question, you have to first make a choice. What equation do you want to use? Then you have to use it. So, you showed 3. Which equation did you use? You see, right here, right now, what did you say? That's a problem. Don't think. And you will not have a problem. You have to choose an equation which relates speed and some other feature of this system which you can clearly see. So please, first I want to see the distribution. And you please now choose the equation and write it down. This is equation number 6. So we had a distribution when answer number 2 was winning. Okay. So please tell me which equation do you want to use? Short or long? No? First of all, that's a common sense. Don't start from harder equations. They harder. Don't start from complicated things. Start from easier things. Try first, easiest, shortest, see if it works. If it doesn't, in that case, you can move on to the next one. Shortest has only 2 variables, A and V. Well, in this situation, we should rewrite it as area at point number 1 times speed at point number 1 should be equal to area at point B times speed at point B. Now, we should say something about these 2 areas. And what should you say? Well, area is a number, and if we need to compare 2 numbers, we only have 3 options to choose from. So, is area 1 greater than area B? Less? The same. When the area is the same, that automatically means the speed must be the same. So, it doesn't matter what is happening. It doesn't matter what we're doing to this fluid. Doesn't matter how we bend the pipe, dig it in, dig it out. Doesn't matter. As long as the area at 2 different points in the pipe, same, the speed of the flow will be the same automatically, always. What will be different? Well, pressure has to be different, of course. For example, now, if we write the Bernoulli's equation, the long one, what should we write? Then density speed 1 squared over 2 plus potential energy density G height 1 plus pressure 1 should be equal to density speed squared over 2 plus density gravity height number 2 plus pressure 2. Now, at point 1, the tube is open to the atmosphere. So this pressure is atmospheric. And we can now set the origin at the point B at the lowest location, which makes height number 2. Well, do I have any? No, I don't. I want to insert a slide. Okay. Spout, tube, so density speed 1 squared over 2 plus density G height 1 plus P atmospheric should be equal to density speed squared over 2 plus 0 plus P at point B. This is the equation. And now we can make it simpler. And every time when we can make something simpler, we have to make it simpler. So how can we make it simpler? We just said that speed number 1 and speed at point B are equal to each other. This statement hasn't been used yet, so how can we use it? By canceling energies. And now we can calculate the pressure at the lowest point, which is going to be atmospheric, plus additional pressure due to the water above it. Again, that's just an illustration. So that's the answer, and more examples. Good. A rectangular pipe with a given cross-sectional area. So we have meters and centimeters. That means I want to use international system of units just for the sake of safety. 10 centimeters, 0.1 of a meter here, 0.1 of a meter there. And the speed equals 2 meters per second. We need to calculate mass flow rate. The mass flow rate, by definition, is equal to amount of fluid in kilograms traveling every second. But we reasoned through this situation, and we derived an equation which we can use to calculate it immediately. If it's water, density equals 1,000 kilograms per cubic meter. Speed is given, so area of a rectangle equals 0.1 times 0.1 height times width. That's it. That's going to be 20 kilograms per second. That's it. The straightforward application of the equation we have derived from the definition. We didn't use the definition. When would we use a definition? If we would have to calculate how much of this water travels, let's say, in an hour. In that case, the amount of water will be equal to mass flow rate times time. So if we know that every second travels 20 kilograms, and if we need to find out how much travels in an hour, we just have to use 3,600 seconds. 72,000 kilograms in an hour. That's it. Okay. What else? Water travels through a hose with a given speed. We know the diameter of the hose. Then we attach in a nozzle, and it travels faster. It's like if you squeeze your garden hose, you can see that it shoots longer distance, which means it leaves the hose at faster speed. Okay. So this is the situation. The area changes from a diameter number 1, which is 2 centimeters below you, to diameter number 2, which is unknown. But the speed changes from 5 meters per second to 10 meters per second. Well, what equation do you think should we try first? The first one, the short one, the continuity equation. A1 V1 equals A2 V2. How do we calculate area of a circle? Pi, a half of a diameter squared. And now it's the same equation for a different area. Well, first of all, we can simplify it by canceling out number pi. Now, I can start using, end. I can cross out both 2's, 2 on the left and 2 on the right. So my equation for the second diameter now says it should be equal to the first diameter squared and multiplied by a ratio of the speed number 1 over speed number 2. Hence, my diameter will be equal to square root of all this. Hence, I can write it like this. First diameter times this ratio. Now I can start using numbers, and actually I can use centimeters. 2 centimeters times this ratio, 10 over 5, and units of speed getting cancelled. So the result is 2 times square root of 2 centimeters. No, what did I do wrong? Five over 10. No one says anything. It's Friday. Yeah, I understand. It's 5 over 10. 5 over 10. So 2 divided by square root of 2 centimeters. How did I know I make a mistake? I know my diameter number 2 should be less than diameter number 1. So I see it doesn't work. Again, Well, after this class, I will have to talk to my brain. We have an extra question. B. If instead of the nozzle we attach a shower head, okay, what will happen? First, it's a new situation, so it requires a new picture. So we still have exactly the same initial diameter, and now we are attaching a shower head with many holes in it. It doesn't affect the fact that mass flow rate should remain constant or volume flow rate should remain constant. Not at all, which means we still can apply the same continuity equation. However, now, this area should represent the total area available for fluid to flow through. This area now just should be equal to the area of a single hole times the number of those holes, nothing else. So the equation which we need to solve for the unknown speed, which is the speed number 2, is very simple again. And since for part B, we know the number of holes, we know the diameter of each hole, and we know initial speed, and we know initial diameter. We know everything. We just have to plug numbers in and finish calculation. Very straightforward problem. Well, at least I want to start this problem. A big horizontal pipe lies on the ground, and then it reaches a tank. So the water is being brought above the ground to fill up the tank. And the rest so far is not important. We will ask ourselves what we know and how to use it later, after first we draw the picture and write both equations and see how they work, what they connect. So the ground level has a pipe on it with a given diameter. And the pipe, so there's a tank, which is not a part of a problem. It's just a part of a situation in general. To fill it up, we have to raise the pipe, and now water falling down in the tank. Now, it's a tall tank, like oil tanks. It's 20 meters above the ground, and the diameter actually, oh, my picture isn't really right, because the diameter is twice, so it's getting wider. So that's an easy fix. I want to draw a wider pipe. Water, 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 water. So the new diameter is equal to 80 centimeters. Okay. Now the atmospheric, it's not atmospheric, it's actually twice of that. The pressure pressure at the bottom is 2 atmosphere. Okay, so it's even more complicated. So the pressure at the top is not atmospheric. So probably it's a closed, completely closed. Maybe it's a toxic, toxic water. Yeah. So the pressure is being maintained at a given number. Okay. That's all we know. By the way, I didn't mention it, but there was a slide which says when we calculate pressure, we use pressure for calculating anything else. Here in the classroom, the atmospheric pressure is taken just to 10 to the 5th pascals. But to solve a Weber sign problem, you should use a more accurate value. For the Weber sign, the atmospheric pressure for the Weber sign, I think it's 101.3 kilopascals. There is a note which says it, so just keep an eye on the value. Yeah. Here, for us, atmospheric pressure is 10 to the 5th, so the pressure at the bottom is 2 times 10 to the 5th pascals, and this is 6 kilopascals, so 6 times 10 to the 3rd pascals. Done. Now, of course, we have to write 2 equations which relate to speed number 1 and speed number 2, which relate kinetic energy at the first level, potential energy at the first level, pressure at the first level, and kinetic energy at the second level, potential energy at the second level, and pressure at the second level. And of course, we can make this simpler by choosing the origin at the ground. Now, let's count what we know. We know area, number 1, area, number 2, pressure, number 1, pressure, number 2, height, number 1 and height, number 2, and density. What we don't know neither speed number 1 nor speed number 2. Well, what do we have to do? Solve the system because physics is done. This is a not very common situation when physics is much easier than math. Because in this situation, to solve this system, you have to solve 2 equations, one of which is quadratic equation. And you have 2 options to do that. Number 1, just solve quadratic equation using discriminant quadratic formula. Number 2, you can try to use approach we used in the past for the absolutely elastic collision when we had exactly the same situation, the law of conservation of a linear momentum, which linear mathematically, and the law of conservation of energy, which quadratic mathematically. So either way, it should work for you. And I just don't have time now to finish this mathematics, but you know what to do. So now we are done for the week. Thank you very much. So I'm going to go to do my office hours until 11. At 11, I'm going to leave. But then at 11:30, teaching fellows start coming back. So please use office hours. Again, some exams. Don't forget to sign in, please. Thank you. Still, how do you open it? You have to put air in it. Let it in. Be careful, just don't splash this one. And just place them anywhere, you know, thank you. All right. Yes. Yes. Because everything else in those equations uses International System of Units, meters per second, kilograms per cubic meter, you know.
That means that the density of water, it's not 1, it's 1,000.
1,000, yes.
Okay, thank you.
Yes.
I have a quick question about Blackboard. When
Blackboard?
will you get back to us about the participation grade?
Maybe today, maybe tomorrow.
Okay. And the regrade, is it on Blackboard or should we?
What do you mean by regrade? Your current grade has, you know, certain value in it. I will go through the list of all. Oops, what did I do? No. All people who sent me a request, and I will change that value to a new value. It's going to be the same column with a new number in it.
For both the exam and the participation grade.
For participation grade. What do you mean?
Exam, I got an extra point after the regrade, so.
It's already there.
Perfect. Thank you.
Can I ask you a
Yes.
question?